The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And by the Corporation for Public Broadcasting. And by contributions to your PBS station from viewers like you. Thank you. Additional funding is provided by Millicent Bell through the Millicent and Eugene Bell Foundation.
22 seconds.
The most ambitious planet hunter ever built sits on a launch pad at Cape Canaveral, Florida.
T-minus 5, 4, 3, 2, engine start, 1, 0.
Over 2 decades in the making, it is about to radically alter what we know about our galaxy.
0-3. Burning out of the solids. Look for separation.
Meet the Kepler Space Telescope. Its mission, to detect alien worlds orbiting distant stars and to discover if any of them could be a suitable home for life as we know it. Project scientist Natalie Batalla has lived with the Kepler mission from the very first moment.
To watch it launch was really quite something. This feeling that after decades of planning, it was finally happening. It was going up there. That was a tremendous moment.
Launched in 2009, this incredible optical telescope has revealed that planets are far more common than we ever imagined.
What's amazing is not just the number of planets that Kepler has found, but the types of planets.
Of the 3,500 potential planets that Kepler has spotted, some seem familiar. Huge gas giants, similar to Jupiter or Saturn. Or smaller rocky worlds that could be like Earth, Venus, Mars, or Mercury. But others are straight out of science fiction. Like Kepler 16b, which orbits a double star, just like Luke Skywalker's home planet in Star Wars. Even more bizarre is Kepler 10b. It orbits so closely to its sun that the surface is a vision of hell.
Kepler 10b is a scorched world that's got an ocean bigger than the Pacific Ocean, that it's an ocean not of water, but of molten lava. The surface temperatures in excess of that required to melt iron. So this is a blowtorched world.
But for Kepler, these oddities are just a sideshow. Because its primary mission is to find a planet that might have the right conditions for alien life. A planet like Earth. Now, Kepler might be closing in on just such a world. The Kepler data suggests that potentially habitable planets are out there. And applying the principles of biology and evolution, scientists are even beginning to guess how ETs could have adapted to their environments.
The best speculation recognizes that there are rules to the game. Any life that we can contemplate is going to be subject to the laws of chemistry and physics.
Kepler is finding worlds that, as far as we can tell, have the right environment, the correct temperatures suitable for life as we know it.
Kepler is unique among space telescopes. Unlike the Hubble, which turned its gaze far and wide and sent back stunning images of the cosmos, Kepler is designed to stare fixedly at one small patch of sky, taking the same snapshot day in and day out for years on end. It began, as with any new telescope, with what astronomers call first light.
Kepler's first light image came down to us at NASA Ames about 24 hours after we ejected the disk cover. As it filled my computer screen, the image that came to my mind was like champagne filling a glass, with all of these stars being the little bubbles. It was very exciting. Every single tiny dot that you see is a star that is in the field of view of Kepler.
Kepler is focused on a small patch of sky near the constellation of Cygnus the Swan.
In that area of sky are 4.5 million stars in our galaxy alone.
But Kepler isn't looking for stars. It's looking for planets that orbit the stars. But that's a problem, because Kepler can't directly see planets. Planets are much smaller and dimmer than stars. They get lost in the glare. So Kepler is looking for something called a transit, which occurs when a planet passes in front of the star. As it does so, it dims the light by a fraction. That dimming is what Kepler is designed to detect. It's a principle that can be illustrated with a distant tower and a spotlight.
Okay, let's imagine that there's a moth flying around that spotlight. Could we ever hope to see the moth? No way. The moth, although it does reflect a tiny bit of the spotlight's light, it's far too feeble for us to see that.
Since the light reflected off a planet is typically 10 billion times fainter than the light emitted by its star, detecting a planet might seem impossible. But Kepler has a way around that problem.
If the moth passes in front of the bright light, a little bit of the light that was going to reach us obviously gets blocked by the moth. Then we are able to detect the moth by measuring very carefully that very subtle change in the total brightness of the spotlight.
The bigger the moth, the more light it blocks, and the more the light dims.
In exactly the same fashion, that's how we can detect small planets orbiting other stars and even measure their sizes.
That's Kepler's primary mission, to watch thousands of stars for signs of a transit. Scientists plot the brightness of each star in Kepler's view on a graph to see how it changes over time. This is an actual plot of one star over 2 weeks. Sure enough, every 3 days there's a tiny dip in brightness, revealing a planet orbiting this star once every 3 days. Just like the moth, the bigger the planet, the more light it blocks. In this plot, a huge planet transits in front of its star, causing a much larger dip. Right from the start, Kepler saw stars dimming. By June 2010, 15 months after launch, Kepler had found over 700 potential planets.
The sheer numbers of planets out there is really quite stupendous. Here you see just a small sample of them. And the planets range in size from, a half the radius of the Earth up to things that are several times larger than Jupiter.
Already, Kepler's discoveries are changing what we know about alien planets.
Kepler has revolutionized our view of planets and planetary systems in our galaxy. It turns out that any kind of planet is possible within the laws of physics and chemistry. Any planet you can conceive of can exist in any location in a planetary system.
Extrapolating from the Kepler data, some estimates put the number of planets in the universe in the trillions. But what everyone really wants to know is, do any of these planets have life? To answer that, we have to go back to the basics and ask, is the universe full of the same stuff everywhere? Are the elements needed for life as we know it commonplace? The lightest elements, hydrogen and helium, were made in the moments after the Big Bang. Other elements are made in stars, a product of nuclear fusion during the star's normal life cycle, or produced when some stars explode as supernovas, scattering these essential building blocks into space.
Every molecule in your body, every element in your body was generated sometime in the distant past by processes within stars.
Among the most common are the elements that are essential to all living things on Earth: hydrogen, oxygen, carbon, and nitrogen. Life could be anywhere or everywhere in our galaxy. But where should we look? Since planets are proving to be so abundant, Chris McKay thinks we might as well search for life that follows rules we already understand.
I know how to search for organic material. I know what the signatures that would be important are. So the search for life starts off following water, following carbon. Not because we can prove that that's the only way to do it, but because that's the only way we know how to do it.
Sifting through the Kepler data, scientists have made a deliberate decision to look for planets that resemble the one place they know can sustain life: the Earth.
We know that the Earth is habitable, indeed inhabited, and so surely there's some drive to find another Earth-like planet elsewhere in the universe.
Humanity is on a quest to find life. Kepler's objective is first to find out if planets like Earth, where we have this one example of life, if planets like that exist.
Earth, as we know, is teeming with life. Organisms have evolved to exploit every niche, from beneath the waves to the highest mountains. So what's so special about our pale blue world? For most scientists, the key feature of Earth is the presence of liquid water on its surface. Chris McKay has spent years studying the relationship between life and water.
Well, the question is, can life survive without water? Well, this is a place to find the answer to that question. This is a desert.
In this baked dry sand near the Mojave Desert in California, Chris is looking for critters that can live without water. One possible candidate are these small black patches, which are in fact alive.
It looks like a black flat rock, but in fact, it's a layer of photosynthetic microorganisms.
But Chris has discovered that although they look bone dry, they actually require water.
The microorganisms have solved the problem of the lack of water in a very ingenious way. The organisms secrete organic materials which help to hold water. They make little super sponges. And so the rare moisture that's there, they can hold it. They can hold it longer than the normal sand. These organisms have created a little tiny microhabitat in which they live.
Chris has studied organisms across the Earth. In the dry valleys of Antarctica, and in the Atacama Desert in Chile, the driest desert in the world. And everywhere, he's found life using similar survival strategies.
We have never found an organism on Earth. The driest, coldest places, and we've looked, and boy have we looked, we've never found an organism that can make do without liquid water.
So life as we know it needs liquid water. Fortunately, water is made of two of the most abundant elements in the universe, hydrogen and oxygen. We've even detected water vapor in clouds of gas in outer space. What's harder to find is a planet that could have liquid water, where the temperature is warm enough to melt ice, and yet below the point where water boils to steam.
The sun is like a fire. It provides light, and through that light, warmth. And that warmth is what keeps the planet warm enough to support liquid water. If it's too far from the sun, the water will be ice. If it's too close, the water will be steam. So it needs to be right in that zone where the water can be liquid. Sometimes we call it the Goldilocks zone. It's not too hot, it's not too cold, it's just right.
Kepler's core mission is to find Earth-sized planets in the Goldilocks zone. Remarkably, this data that shows the timing of each transit is also the key to finding out how hot a planet might be. The more frequent the planet transits, the hotter it is.
When a planet is very close to the star, it's going around quite rapidly. The period is very short. It can go around in weeks even around the central star. As the planet is further away, it takes much longer.
A planet that orbits once a week will be close to its star and very hot. A planet that orbits every 10 years will be very far away and too cold. So scientists were looking for a planet orbiting a sun-like star roughly once a year, like Earth. On May 12, 2009, just 3 days after the spacecraft started collecting data, it saw the light from the star Kepler-22 dim ever so slightly. 10 months later, it dimmed again. If it happened once more in another 10 months, it would confirm Kepler was seeing a transit. Sure enough, on December 15, 2010, the star dimmed once more. Kepler had discovered its first planet in the habitable zone. Kepler-22b, over 600 light-years away.
Kepler-22b was the first confirmation of a planet that is at just the right temperature. So it's in the Goldilocks zone. It's orbiting a star very much like our own sun.
The researchers can use the amount of dimming to measure the size of the planet. It works out at about 2.4 times the radius of Earth. So now comes the next mystery. What kind of planet is Kepler-22b? What is it made of? The key to a planet's composition is its size. When planets form, they start off solid, made of rock and ice. If they become big enough, they're able to hold on to huge amounts of gas, hydrogen and helium the most abundant. These become the gas giants, like Jupiter and Neptune. Smaller planets like Earth are primarily rocky and can only hold on to a thin atmosphere. Kepler-22b is in the middle, bigger than all the rocky planets in our system, but smaller than the gas giants. So is it mainly gas or rock? Astronomer Jeff Marcy is attempting to find out. Tonight, he's using the Keck telescope in Hawaii, which he's operating via video link from Berkeley, California, over 2,000 miles away.
So Jeff, I just opened up and did an autofocus. We've got about 0.85 arc second seeing.
That's great. Fantastic.
And we're set up and ready to go on your first target.
Tonight we're going to be observing Kepler 22b, the planet, which is still somewhat mysterious. We don't know whether the planet is rocky like the Earth or gaseous like Jupiter and Saturn.
To answer this question, Jeff is using a very different way of detecting planets. Nicknamed the wobble method, this technique was used to find some of the first exoplanets. And it's also used to find out more about the planets discovered by Kepler.
We can detect planets around other stars even without seeing the planets by watching the star. Let's create a star. And of course, we'd like a planet orbiting that star. Now what's interesting is that the planet not only orbits the star, but the star is yanked on gravitationally by the planet. So we see the star wobble around, and we can detect this with our telescopes here on Earth.
The Keck telescope can see if a star is wobbling backwards and forwards in response to a planet we can't actually see.
But even more beautifully, we can measure the mass of the planet, because the more mass of the planet orbiting the star, the more violently that star is yanked on gravitationally.
If the telescope detects a large wobble, it means a massive planet is orbiting the star.
We're heading to the Kepler field now. So I'm going to set the exposure meter.
Jeff takes aim at Kepler 22.
That gives us Doppler shift precision of about 1.5 meters per second. So we'll be able to measure the speed of the star to within plus or minus human walking speed. Here we go. And there it is, Kepler 22. Looks beautiful.
Even with this high level of precision, Jeff fails to find a measurable wobble, which means that the planet is not extremely massive.
So far, what we can tell is that the planet is probably not purely solid. It's not a big ball of rock.
Kepler 22b could still be a gas world, a kind of mini Neptune. But there's another possibility that's even more intriguing. This planet might be unlike anything in our solar system. A water world.
We do know that as long as the planet is over 7 times the Earth's mass, it could possibly have liquid water at its surface. So Kepler 22b, despite being a relatively big planet, is still in the potentially habitable category.
From the study of other planets, all of those somewhat larger than Earth planets have lots of water and also perhaps some atmosphere. So by association, the bet is that Kepler 22b will be a rocky planet with a very dense and thick ocean.
If Jeff is right, this would be a planet completely covered in water. It's the perfect planet for a paddle. Jeff can imagine what it would be like to kayak on Kepler 22b.
If you were kayaking on Kepler 22b, you'd look overhead, you'd see a host star that would remind you of our own sun here, a yellowish star about the same size as our sun. The gravity of the planet might be a little higher, a little lower than the Earth, but not so different.
But look beneath the surface, and this ocean is unlike anything on Earth.
The ocean would be thousands of kilometers thick. There would be no ocean floor to dive down and visit because it would simply be too far away.
Kepler 22b could have all the ingredients for Earth-like life. Energy is plentiful in sunlight from the nearby star. The necessary elements, like hydrogen, oxygen, carbon, and nitrogen, are commonplace throughout the galaxy. But for life to occur, these elements would have to form into a molecule with a very special property. A molecule that can self-replicate like DNA.
Life is a chemical system capable of Darwinian evolution. We need molecules for life that contain information. We need molecules that can mutate so that that information changes and that can be inherited. I suspect that carbon is going to be the stuff of life, and there will be information-containing molecules such as DNA.
Even here on Earth, we don't know how DNA first came to exist. But even if the creation of a molecule that works like DNA is unlikely, life may have sheer numbers on its side.
It may be that only one planet in a million will give rise to life. But on the basis of Kepler, some people have suggested that there might be 10 to the 19th planets in our galaxy or in nearby galaxies. That's a very big number. And so the probability that life exists elsewhere is pretty high.
It's this emerging statistical fact that leads many scientists to be confident that extraterrestrial life does exist.
Is there life elsewhere? Well, our galaxy alone has 100 billion stars.
If DNA, or a similar self-replicating molecule, has formed on any of those planets, life could have been around for some time.
If we go back to the very oldest sedimentary rocks on our planet and look for the signature of life, it's already there. And that tells us that life arose early.
But early life was limited to simple single-celled organisms. Microbes had the Earth to themselves for billions of years before complex life evolved. It may be that microbes rule our galaxy as well.
The most probable life on other planets would be something much more similar to bacteria than to you or me.
Of course, we don't know how likely it is that complex life would evolve on an alien world.
It's still very much an open question as to whether life could get started in such a water world. But over billions of years, if the climate was stable enough, evolution will have had the chance to get beyond microbial life to forests of complex advanced trees.
Could plants adapt to life in an endless ocean?
On a water world, the main challenge that these plants are going to face is remaining buoyant. You can't start sinking down if you want to float, perhaps by having bladders filled with gas that help you to buoy up in the water.
While scientists can speculate about life on Kepler 22b, for now there is no way to confirm that there is water on its surface. Fortunately, it isn't the only potential life-supporting planet Kepler has found. On February 28, 2012, nearly 3 years after launch, NASA announced over 1,000 potential new planets. One of these was orbiting the star KOI 2626. This potential planet is about 1.5 times the size of Earth, small enough that it's likely to be rocky. But there's a problem. It doesn't orbit a star like our sun. It orbits a very different kind of star.
When I was a kid, I was told in school that the sun is an average star, which is a complete lie. The sun is not an average star. Most stars in the galaxy are much less massive and put out much less energy than the sun. And we call these very low-mass stars M dwarfs. Our sun is yellow in color, very massive, very large, and compared to it, these low-mass M-dwarf stars are tiny. They're only about 10 or 20% the size, 10 or 20% the mass, and they only put out 1/1000th the amount of energy.
M-dwarf stars, also known as red dwarfs, make up over 3/4 of all stars in the universe. Because the star is so small, it's easier to spot a small planet orbiting one. Even though an Earth-sized planet covers only about 0.1% of a red dwarf, it typically dims the light by an easy-to-see 1%. Dave Charbonneau and his team have searched through the Kepler data, and they found that more than half of all such stars have planets Earth-sized or a little larger. But could a planet orbiting such a dim star be warm enough to have oceans of water and even life?
An M-type star provides much less sunlight than our star. To get the same amount of warmth, just like this dimmer fire, you have to move in closer. There's still a habitable zone. You can get close enough to the star that it's warm enough for liquid water.
KOI 2626.01 orbits its red dwarf star once every 38 days. But being so near to a star can create a strange situation. Gravity from the star pulls more strongly on the closest side of the planet. A slight drag that can cause one side to always face the star. Astronomers call this tidal locking. This alien world would have a light side on which the sun never sets, and a dark side on which the sun never rises. At first, scientists thought that this would make the planet impossible for life because it wouldn't have an atmosphere.
When we first conceived of the notion of a tidally locked planet, even in the habitable zone, the thought was, well, on the dark side, it's going to be very, very cold. So cold that the atmosphere could condense out completely. All the carbon dioxide that would normally be in the atmosphere would be present as ice, forming a giant polar cap on the dark side. Ice like this. This is a chunk of carbon dioxide.
But atmosphere expert Kevin Hang wasn't so sure. He builds computer simulations of alien atmospheres. He's a kind of interplanetary weather forecaster. Hang used what we know about the red dwarf planet to simulate the atmosphere. And this is what he came up with. A map of the whole planet laid out flat, the colors representing the predicted temperature.
What you're seeing is a temperature map near the surface. Right in the middle of the map is the point where the temperatures are expected to be the highest.
And this temperature difference between the hot side and cold side has a profound effect on the atmosphere. Here on the dark side, the air cools and sinks, spreading out around the planet. That creates a wind that blows along the surface to the hot side. Here, the air heats up and rises before returning to the cold side. So if this planet has an atmosphere, it would have a permanent planet-wide wind system. This reduces the temperature difference and keeps the atmosphere from freezing, which means that the planet might be habitable after all, with a stable atmosphere and in some places, a pleasant climate.
You probably want to live close to where the day side transitions into the night side, the so-called day-night terminator, where temperatures are between 10 and 20 degrees Celsius. So a good spot for real estate.
If there is plant life here, it would have to adapt to an endless deep red sunset. Here on Earth, most plants capture energy with chlorophyll, a green pigment adapted to harness the yellow light from our sun. But on a red dwarf planet, with its red light, an alien plant-like species might adapt to produce different pigments. Nancy Kiang is trying to work out what those alien plants could be like. One clue is to be found in the marshes of New England.
The sandy areas you might think are just dead areas with no plants, but actually there's life teeming underneath.
Living in the sand are layers of photosynthesizing bacteria.
What we see here are different kinds of bacteria that are photosynthetic. Each layer has different pigments that absorb different wavelengths of light.
The bacteria in the top layer are green. They use the same chlorophyll that plants do because they receive the full spectrum of sunlight. But many of those frequencies get absorbed, leaving the lower layers with a different color of light. So they have evolved new photosynthesizing molecules adapted to that different spectrum. Studying these different molecules allows Nancy to imagine what sort of pigments would work best on alien worlds bathed in the dim red light of a red dwarf. It leads to an intriguing suggestion.
Very likely these plants will try to absorb as much visible light as they can. So these plants, to our eye, might look black.
Black, because the plants would need to absorb as much energy as possible from the weak sun.
Plants might find the situation actually easier to contend with because the sun isn't moving through the sky. You can just point yourself like a solar panel towards the sun. But one of the other features of a tidally locked planet would be the fearsome winds blowing constantly in the same direction. So maybe a flat panel wouldn't actually end up being the optimum design, and you want to be a bit more flexible and giving to allow the wind to kind of blow through your perhaps fan-like shape.
If there are plants, could there also be alien animals on this planet? From the wide variety of creatures that exist on Earth, we know that many seemingly bizarre creatures are possible.
It's fun to speculate about what life might look like on another planet. I think it's legitimate science insofar as it tells us that there are rules to the game. Any life is going to be subject to the laws of chemistry and physics.
Based on what we know about life in our world, and from what we know about the environment on this distant planet, scientists are beginning to imagine what alien animal life might look like.
On Earth, we find filter feeders, life that filters particles or little grains of food out of the water as it wafts past them. On a planet like this, we might find a similar strategy on the land. So maybe we'd find something like land whales that aren't filtering out plankton from the sea like the whales in our oceans, but are great big static animals that try to filter out particle matter from their wind to feed off.
Even though scientists speculate about how life might survive on truly alien worlds like this, most still believe that our best hope of finding life that we might recognize lies in finding a rocky planet, a similar size to Earth, that orbits a sun more like our own. It's a challenge of astronomical proportions.
A planet as tiny as an Earth transiting across the disk of its star is going to produce a change in brightness of just 1 part per 10,000. Imagine the tallest hotel in New York City, and everybody has their light on, and one person in this hotel lowers the blinds by about 2 centimeters. That's the change in brightness that we're trying to detect from the transit of a planet as small as an Earth passing in front of a star the size of our sun.
So Kepler scientists scour the data for signs of a truly tiny dip, evidence of an Earth-like planet. And they find something promising around star KOI 701, 1,200 light years away. The Keck telescope confirms that there are at least 3 planets orbiting the star.
The third planet out, that planet is in the habitable zone. But it's also large, like 22b. It's like Kepler 22b. It's, probably a water world.
The team was about to go public when something extraordinary happened.
So 701.03 was done. In the bag, nice ribbon tied around it, ready to go off to the publisher for publication, when we got an email from one of our team members telling us that he'd spotted what looks to be Another interesting signal in the data.
What Natalie's team member had spotted at the last moment could turn out to be one of Kepler's most exciting discoveries. It looked like KOI 701 didn't just have 3 planets orbiting it. There were 4. And this new potential planet was in the right place and the right size.
We examined the data more carefully, and there is another planet that is smack in the habitable zone, and it's only a little bigger than the Earth.
It was exactly what Kepler had been searching for. A planet in the habitable zone, small enough that it could be made of water and rock, like the Earth.
And so this is something you could stand on, something that's rocky.
This might be the first truly Earth analog around a sun-like star that's ever been found.
The planet, today confirmed as Kepler 62f, is over 1,200 light-years away. Even our fastest spacecraft would take many millions of years to reach it. But this could be the most Earth-like world Kepler has found.
And that's the amazing planet that has the hairs standing up on the back of my neck.
If this planet has oceans of water and rocky land masses, then the possibilities for life here could be as numerous as they are on our own planet.
On our planet, we began with simple bacteria, and today we have a planet that has 10 million species of animals, plants, fungi, kelps, all sorts of things.
In the oceans, the environment could be surprisingly similar to that on Earth. The density and properties of water are dictated by the laws of physics, which are universal.
What we might expect is for the aquatic or the marine life to be actually pretty similar, pretty familiar to what we know on Earth. Because the main consideration is being able to move through the water as efficiently as possible. So you want to be hydrodynamic, you want to be streamlined in your shape. And a very good streamlined shape is known as fusiform, you'll be kind of bullet-shaped, just like most fish on Earth.
This ocean could be home to a complex ecosystem with different sizes of organism filling different ecological niches. But because this planet is 40% larger than Earth, it's likely to have stronger gravity. So what might we find on land?
Animals will respond to the increased gravitational pull on a larger planet. And so they would want to have body plans which are also very strong, so with column-like legs to support their increased weight.
On Earth, all vertebrates have a maximum of 4 legs, because all animals with a backbone evolved from a fish that had 4 fleshy lobed fins. But could aliens have more legs? That's what Bill Sellers wants to find out. He usually looks at extinct species like dinosaurs by recreating their structure in a computer. The same technique can be applied to an alien body plan.
When we have an alien life form, we treat the shape of the animal as the framework of the robot. We add motors to actually drive the creature. And then the trick is that we get the computer to learn how to be the most effective driver for this particular shaped animal.
Bill is investigating how life might move in a high-gravity environment. The computer model he's using is called a genetic algorithm. First, he creates an 8-legged alien. Then, the computer generates hundreds of random movement patterns and tests them out.
This is a moving forward start. But as you can see, what happens if it gets the pattern wrong, then although it's still moving its legs, it's lost all forward velocity and actually is starting to go backwards in a very unstable way. Other examples of failures, for example, this one, what happens is the front pair of legs trip over and then the whole thing nosedives, and because of where the weight is, the back legs are up in the air and spinning round. So again, this is a complete failure and we wouldn't work from those.
But the computer can take the best of those random patterns and combine them to produce new variations. It echoes the process of natural selection that drives evolution.
After the evolutionary process is finished, we end up with these very stable, very efficient gates. What the work has shown is that this eight-legged creature mechanically could cope with higher gravity.
Bill's work shows that it is mechanically plausible that this new Earth-like planet could have animals with 8 legs walking across its surface. If this planet does have complex animals, could it also have intelligent life? For astronomer Jeff Marcy, this is the ultimate question.
We really don't know. First of all, we don't know how commonly life gets kick-started. And secondly, we don't know how commonly it evolves into intelligent life.
The probability of intelligent life evolving on another planet is perhaps the greatest unanswered question. But there are hints on Earth that intelligence might be the exception, not the rule.
Sharks, like the ones we see here, have ruled the seas for 400 million years, and yet their brains are no larger than peas. How could it be that after 400 million years, sharks have not developed a higher intelligence? And of course, the answer must be that high IQ sharks compete no more successfully than the less intelligent sharks among us. And that tells us something frightening about life elsewhere in the universe. Perhaps the intelligence of which we humans are so proud is not an attribute that is strongly favored in Darwinian evolution.
If Jeff is right, human intelligence may be the result of a very unusual set of circumstances that just happened to make our ancestors develop bigger brains. But others, like Sarah Seeger, are more optimistic.
It's a tough call about whether or not there's intelligent life around any of the nearest stars. I believe there is intelligent life out there somewhere in the galaxy, and that a future generation may be able to establish contact.
While the chances of intelligent life evolving may be small, the number of places it could be is huge.
About 900 of these planet candidates are twice the Earth's radius or smaller. So what this collection of exoplanet candidates is telling us is that small planets, planets like Earth, might be common.
Based on the Kepler data, scientists estimate that at least 1 in 6 stars has an Earth-sized planet. There could be upwards of 17 billion Earth-sized planets in our galaxy alone.
Well, we are at a remarkable moment, actually. The Kepler Space Telescope has identified several thousand planets. But what's unexpected and remarkable is that we're finding planets that are a little bit larger than the Earth, that, as far as we can tell, have the correct composition, rock and water, suitable for life as we know it.
Kepler has shown us how commonplace planets outside our solar system are, suggesting our galaxy may have other places suitable for life. Kepler continued to collect data until May 2013, when the guidance system failed, and it lost its steady lock on the stars it had watched so keenly. But the hunt for alien planets is far from over. Kepler may have a second life, using pressure from sunlight to keep it oriented. And in coming years, new planet hunters will take up the quest, exploring the age-old question, are we alone?
Facebook and Twitter.
February 1930. Clyde Tombaugh, 24 years old and fresh off a farm in Kansas, patiently scans photographic plates at the Lowell Observatory. He finds a tiny speck that turns out to be a new planet called Pluto. But in the 75 years since then, our close-up views of Pluto and its giant moon Charon still only come from the artist's imagination. Every other planet has been visited by NASA spacecraft, and the post office has issued stamps to commemorate their close encounters.
Of course, for Pluto, because there have been no mission to Pluto, the U.S. stamp says not yet explored. We aim to see a new stamp issued.
We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
January 19th, 2006. NASA's New Horizons mission to Pluto successfully lifts off from Cape Canaveral, traveling faster than any previous spacecraft. In just 9 hours, New Horizons passes the orbit of the Moon and begins a 9-year voyage to Pluto. February 28, 2007. The spacecraft zooms past the giant planet Jupiter, getting a 9,000-mile-per-hour gravity assist and cutting 2 years off its journey.
Spacecraft is outward bound from Jupiter, and we're on our way to Pluto.
All right.
The Jupiter flyby was a dress rehearsal for Pluto.
We got the night show. Oh wow, look at that. Oh yeah.
New Horizons science instruments return detailed images of Jupiter's clouds, moons, and rings. If all continues well, things look good for July 2015 and the Pluto flyby. In the past decade, humans have been making amazing discoveries in the outer solar system.
The very first thing I did is grab my telephone and called up my wife, and I said, I found the 10th planet.
But astronomers continue to debate the definition of a planet and how the new discoveries change our evolving picture of the solar system. So now, the New Horizons mission is perfectly poised to shed light on this question and revolutionize understanding of our cosmic neighborhood. It's the ultimate in discovery and exploration.
We have no idea what the surface of Pluto looks like. So we could see craters, we could see geysers, we could see patches of frost. This is purely speculation. We have no idea what we're really going to see.
Late 2005, the long journey begins. Cape Canaveral, Florida, NASA's Kennedy Space Center. In the Kennedy clean room, the New Horizons spacecraft takes its first short flights. It's just over 2 meters, about 7 feet from the tip of its high-gain antenna to where it joins the rocket, about the size of a grand piano. Fully loaded with fuel, it weighs 1,000 pounds. Not very large or heavy for a planned journey of almost 20 years.
The main difficulty about going to Pluto is that it's so far away. The Earth is almost 100 million miles away from the Sun. Pluto is 30 times that far, 3 billion miles away. To get to Pluto in our lifetimes means it has to go very fast. Its average speed is more than 10 miles per second. And to do that, it had to be light.
One of the unique things about New Horizons is that we built a very light spacecraft and bought a very large launch vehicle. And the combination is ferocious. It gives us a very high flyout speed because we have a very long way to go.
Sprinting away from Earth on launch day, New Horizons crossed the orbit of the Moon in just 9 hours. Apollo took 3 days. The spacecraft reached Jupiter in 13 months. Galileo took 6 years. But even traveling more than 50,000 miles per hour, it will still be 2015 before New Horizons reaches Pluto and Charon.
So it's not that we're dawdling, we have a long way to go.
Why send a spacecraft on such a long and difficult journey into such a challenging environment? For the science team, it's a voyage back in time to see, close up, evidence of how solar systems form from clouds of gas and dust, and how Earth and all the planets were born.
We're going to learn about how planets are built, because what Pluto is a planetary embryo, an object that's partially formed as a large planet, a stage in planetary formation that the Earth went through, that Mars went through, that all the larger planets had to pass through this size scale. But here we see an object that didn't get any further in the case of Pluto.
The National Academy of Sciences rated this mission to Pluto and beyond the most important planetary mission of the decade. That's because New Horizons could rewrite everything we know about the planets of our solar system.
And if you think about the solar system, the so-called terrestrial planets, they're rocky objects in the inner solar system, Mercury, Venus, Earth, and Mars, have a lot of similarities. Then you step out a little bit further and you get into what are called the gas giant planets. These are huge objects which are dominated by large amounts of molecular hydrogen and helium gas. And that's Jupiter, Saturn, Uranus, and Neptune.
And that was it. We sort of stopped there. And then there was the little misfit Pluto at the outer edge of the solar system. Poor little Pluto, all on its own.
Then in the 1990s came a series of discoveries that changed everything. Researchers found more and more icy objects in a massive region of the outer solar system known as the Kuiper Belt.
And once we discovered the Kuiper Belt, everything sort of fell into place. The understanding that, in fact, Pluto and Charon are members of this other class of objects called the ice dwarfs.
And in fact, we think that these ice dwarfs are the most populous class of planetary body in our entire solar system.
That tells us, from that respect, Pluto's not special. It's got lots of company out there.
Ice dwarfs aren't just far out there. In the early days, 4 billion years ago, they may have had a role in shaping Earth and bringing our planet the materials of which we're made.
The collisions within the Kuiper Belt produce the short period comets, which then fall in towards the sun and bombard the Earth, sometimes bringing some of that raw material from which life formed and some of the water that's on the surface of the Earth.
This information about the Earth's birth isn't available anywhere else.
So the key part of that big puzzle of how the solar system formed will come from looking at Pluto, understanding its nature, what it will imply about its formation, how it came to be, and everything about it.
Coming up, with New Horizons safely on its way to Pluto, find out what sophisticated scientific instruments are on board to unravel Pluto's mysteries. For this first ever trip to Pluto, the science team wants to find out the basics. What do Pluto and Charon look like? What are they made of, and what kind of atmosphere exists? Their hunch is that all these questions are connected.
With Pluto, if you want to understand the atmosphere, you have to understand the surface. If you want to understand the surface composition, you have to understand the geology. If you want to understand the geology, you've got to understand the atmosphere. It's all tied together, and so we have instruments to study every aspect of Pluto.
The 7 science instruments on board New Horizons are ingeniously designed. They're small and weigh very little. On average, each uses no more power than a household nightlight, and they're intended to work together seamlessly.
We picked names for most of our instruments. We have Rex and Alice and Ralph, and it's just a happy family.
The black and white telephoto camera called Lori will be used for navigation in the months before closest approach and to study Pluto's surface.
This big barrel is a telescope called LORI, the Long Range Reconnaissance Imager. It's our biggest, most powerful camera in terms of resolution power.
The cameras are key. For over 60 years, Pluto remained little more than a dot. as small and dim as a walnut seen from 30 miles away. In the 1990s, even the Hubble Space Telescope showed just a blurry surface. And this true color image is the best we can do with Hubble and advanced computers. Pluto clearly has a varied surface, but whether these are mountains or craters or polar caps remains a mystery. That's where New Horizons wide-angle camera comes in.
We want to get up close and personal.
Ralph is our main color camera. It's also the camera that's going to take our main global maps of Pluto.
We can get in and map at scales of kilometers and sub-kilometers and even down to tens of meters.
Football field-sized resolution at Pluto. We're going to be able to, to see things thousands of times more precisely than what we've been able to do with the Hubble Space Telescope.
Strangely enough, Pluto's surface seems to have about the same brightness as freshly fallen snow on Earth. It appears so dim only because it's so small and very far away. Equally bizarre, Pluto sometimes behaves more like a comet than a planet. When its eccentric orbit brings it closer to the Sun, the surface heats up and produces a denser atmosphere. Ralph's sister instrument, using a different part of the electromagnetic spectrum, will be studying that.
This is the ALICE ultraviolet spectrometer, which will probe the composition of Pluto's atmosphere and also study its surface.
It measures light with a shorter wavelength than what you and I see. We fly past Pluto, that's the antenna direction. We're going to turn, so the antenna is pointed back at Pluto, back toward the Sun, and we're going to watch as the Sun passes behind Pluto, and we're going to see the sunlight get absorbed at these ultraviolet wavelengths, and we can tell what the atmosphere is made out of at these different heights.
As Pluto approaches and retreats from the Sun, it's thought that there are seasons and weather that resurfaces the planet with fresh, bright ices. Some researchers think this is what creates the light and dark regions, but as yet, no one knows. New Horizons hopes to get to Pluto before winter sets in, and the atmosphere freezes back down to the surface as solid ice. Along its 9-year voyage, New Horizons will also be collecting some very important samples of dust.
What's the big deal about dust? We have dust everywhere. Dust in your house, dust outside, dust all out the solar system. Well, dust comes from the grinding up of material that gets shed and left around. In the case of the solar system, we believe that the dust that's flying around the solar system was produced by the grinding up of asteroids, the grinding up of Kuiper Belt objects, the grinding up of ring particles and so on that is left over from the process of not just forming the solar system, but its constant evolution over time.
So the last of the 7 instruments is a special dust counter. But this instrument comes from a very surprising source. Every part, from logo to detectors, was designed entirely by college students.
Its job is to profile the density of dust particles all the way across the solar system for the first time.
Put it in this big tank, we pump all the air out, it's in a vacuum just in space, then we heat it up and we cool it down, just as it's going to see when it's actually in flight.
And it's not just the extreme cold that engineers test for. The launch itself puts huge stresses on the spacecraft.
These rockets, they're gigantic. They shake a lot. If you've ever seen a paint shaker at a hardware store where it mixes the colors into the paint, that's exactly what the spacecraft is going to go through during launch. One of the things we do is we put the whole spacecraft on a gigantic vibration table, a paint shaker, and shake it. And then test it after that, and shake it again and test it again.
Test phases at APL and Goddard have been very intense. We're running a 7-day-a-week, 3-shift-per-day operation.
Nothing was easy. Even getting to Andrews Air Force Base meant fighting traffic. Leaving home for Cape Canaveral and the final critical months before launch, the engineers in charge were a little nervous.
This is pretty definitely high on the stress level curve. Getting the spacecraft moved from Columbia, Maryland, all the way down to the Cape is pretty tough.
Like packing for a long trip, everything you need must come along. Test equipment, spares, tools.
Everything we're doing is the last time we do it. We want to make sure every bolt is exactly tight and fastened correctly. Everything's been assembled, tested. The records are kept properly because there's no going back. This is a flight build.
Saturday, December 17th, 2005. Spacecraft and third stage in its closed-up fairing, like a giant fragile egg, are placed on top of a huge transporter. With 9 axles and 81 wheels, it's able to raise and lower itself to roll over bumps and up and down slopes without tilting the cargo. Working round the clock, they arrive at Pad 41 before dawn. "75 years after the discovery of Pluto, 17 years after a mission was first proposed, the dream of exploring the 9th planet was now only weeks from launch."
For most people on the project, in a sense, this is the end because it will be built and launched and on its way. But for the science team and the operations team, this is the beginning. This is where we begin the journey. Like a ship, we launch it.
On January 19, 2006, after nearly 2 decades of planning, building, and testing, a picture-perfect launch thrilled the mission operations team back at Johns Hopkins. But the long journey to understand Pluto actually began 75 years earlier, far away in the American West. The story of Pluto's discovery begins here, Flagstaff, Arizona, the Lowell Observatory. Named for its founder, Percival Lowell, a rich Bostonian who was fascinated first by the possibility of water and life on Mars, and then by the search for Planet X, an undiscovered world out beyond Neptune. Pluto was discovered here, and the observatory remains a center of Pluto research today. Astronomer Mark Bowie personifies the ingenuity and persistence it takes to study Pluto.
Part of why I like Pluto so much, because it's a cold, icy place.
Bowie's role on New Horizons is to help find targets far out in the Kuiper Belt, where the spacecraft will travel after it has flown by Pluto and Charon. This homegrown instrument, named Mimir after a Norse god of wisdom, will be placed on ground-based telescopes to study ices on Pluto's surface before the spacecraft gets there. For 2 decades, Bowie and colleagues have used the best instruments available to map the planet. In the mid-90s, he and Alan Stern collaborated in using the Hubble Space Telescope to make the first direct images of Pluto's surface.
Hubble has revealed the first glimpse of Pluto for the first time. And it's exciting to Mark and I and to our whole scientific team to be able to see this object that no humans really could glimpse as a real planet, as a real object in the solar system previously.
In 2002, astronauts placed the new Advanced Camera for Surveys on board Hubble, and Bowie now had data for a new map.
I think this map is probably the best map we're going to get prior to the spacecraft getting there.
Pluto clearly has dramatically varied geology, though the images are still mysterious. But what a transformation from the dot of light that was Clyde Tombaugh's first sight of Pluto 3/4 of a century earlier. 75 years to the exact day and time, Observatory Director Robert Millis shows us how the discovery was made.
75 years ago, Clyde Tombaugh sat at this machine and became the first person to ever see the planet Pluto.
The machine is called a blink comparator. Tombaugh used it to look at photographs of the same patch of sky taken a few days apart. Night after night, he'd patiently expose the large glass plates. Day after day, he'd blink the plates back and forth, looking for anything different from the fixed points of starlight. Decades later, Tombaugh still recalled just how uncomfortable and challenging the search for Planet X turned out to be.
You get cold, you get numb, It took a lot of perseverance, because this gets brutally monotonous.
Blinking back and forward, Tombaugh was looking for anything that shifted position.
The only means you have identifying a planet is going to be small. It's like a small star image. The only clue you have is it shifts position with an interval of a few days in a night's time. That's the only clue you have. So you've got to see all these star images, hundreds of thousands of them, to see if any of them shift position during the interval between the first and second plate.
That small movement was just what Tombaugh saw on February 17, 1930. The arrows were added to show its position a few days apart. It was just what Lowell and Tombaugh wanted to see, a distant planet. After some debate, an English schoolgirl, 11-year-old Venetia Burney, came up with the name Pluto, god of the underworld. PL, of course, were also Lowell's initials. By studying the motion of that dim and distant dot of light, astronomers discovered a Pluto year, the time it takes to move once around the Sun, was equal to 248 Earth years. The angle of its orbit, seen here in silver, was steeper than any other planet. Its distance from the Sun also varied more than any other planet. For 48 years, that was all anyone knew about Pluto. Then, in 1978, astronomers Jim Christie and Bob Harrington analyzed new plates taken at the U.S. Naval Observatory in Flagstaff. Christie noted an elongation of the planet to the north. 1 month later, the bump had disappeared. Blink the images back and forward just like Clyde had done, and you see the bump is moving. Their conclusion? Pluto, like Earth, has a moon. Christie suggested the name Charon after the ferryman of Pluto's underworld in Greek mythology, but preferred to pronounce it Charon, more like his wife's name, Charlene. From the motions of Pluto and Charon, astronomers could work out that the moon was almost half the size of its planet, so large that both objects spin around a central point, their mutual center of gravity, outside Pluto. Pluto and Charon were the first binary planet known in our solar system. Using the basic physics of their orbits and their distance from each other, astronomers were able to calculate their mass and size. Pluto was smaller than our moon, about 1,500 miles in diameter, and had only 1/10 of its mass. Pluto and Charon together would barely stretch across the continental United States. From its size and orbit, astronomers estimated that Pluto is perhaps half rock and half ice. That makes it one of the largest of a whole new class of objects, the ice dwarfs, living out in what's known as the Kuiper Belt. This region is named for Gerard Kuiper, a leading mid-20th century planetary astronomer. Kuiper suggested that the solar system didn't end with Neptune and Pluto, but that there should be a disk or belt of other worlds somewhere way out there. In 1992, from a mountaintop in Hawaii, David Jewett and Jane Liu found the first Kuiper Belt object. They were using new and highly sensitive CCDs, like the sensors in a modern digital camera. But their technique was essentially an updated version of Tombaugh's work. Take carefully registered images of a patch of sky and see if anything moves against the distant stars. This one, QB1, did just that. Jewett and Liu had found the first Kuiper Belt object. It was just a few hundred kilometers across, about the size of an asteroid. In 2002, Caltech astronomer Mike Brown and colleagues found a Kuiper Belt object half the size of Pluto. In 2004, Sedna, another world, 3/4 the size of Pluto. Brown kept on looking, using computers to do the work of Tombaugh's blink comparator.
We do exactly the same thing. Clyde Tombaugh is the one who basically figured out the system for finding these things, but we do it all by computer instead. These are 3 images in a row that are blinking on the screen, just like Clyde Tombaugh would blink. On the morning of January 5th, 2005, I was looking at these very images, and I clicked the button saying this one's no good, and I suddenly see this object here very clearly moving across the frame. in dead center. This is the one where I almost literally fell out of my chair because it's perhaps it's close to being the brightest object we'd ever seen out there, and it's also moving extremely slowly. Slow.
Unlike missions that go into orbit around their target planet, New Horizons is traveling so fast there's no practical way to slow down. After a 9-year trip, closest approach to Pluto and Charon will flash by in less than a day.
This is going to be incredibly nerve-wracking. As we do the encounter, we get one shot at flying by Pluto. That's both terrifying, also very exhilarating.
Pluto is so far away that radio signals from Earth take 4.5 hours to get there, and 4.5 hours back. This 9-hour round-trip light time means computer commands for every aspect of the encounter, from navigation to operation of the science instruments, must be programmed, tested, and uploaded ahead of time.
It's very scary to build a spacecraft and then launch it and not get any data for 9 years. And so it's really key to test out the instruments before we get there.
June 2005, 10 full years before arrival at Pluto. The mission operations team runs a detailed simulation of the encounter, modeled to the split second. To test the spacecraft still more rigorously, the project decides to use the Jupiter flyby to take actual scientific observations. They'd look at the volcanic moon Io. They'd study Jupiter's cloudy surface and aurora.
This will be a wonderful dress rehearsal for the whole process of putting together a complicated sequence. And we only get to do it once at Pluto, so having this practice at Jupiter will be very valuable for that.
January 2007, still another simulation. The Jupiter encounter has mission planners working harder than ever.
So it's more intense than by several orders of magnitude than anything we've done as far as memory usage, which translates to number of commands.
It's more intense actually than our Pluto simulations we did pre-launch. I guess the usual stuff. Axis normal, our SPE is going to range from 7.056 degrees.
The observation starts 10:06:16.
Before any command is sent up to the spacecraft, it's reviewed by a representative of every subsystem, power, thermal, data handling, as well as the science team. One bad line of code can cripple a spacecraft. The Jupiter encounter has 40,000 of them. Every command is run through a series of computers, identical to those up in space, except that this New Horizons mission simulator is safely on the ground in Maryland. February 28, 2007, 45 minutes after midnight GMT. New Horizons closes in on Jupiter. Hours later, scientists and engineers gather at the Applied Physics Laboratory for what they hope will be the first post-encounter transmission from the spacecraft. Mission managers coordinate with researchers across America. Experienced operators stand by at stations dedicated to each instrument and subsystem. The ACE, or Lead Flight Controller, communicates with NASA's Deep Space Network Station in Australia. Alice Bowman is Mission Operations Manager, or MOM. Her professional family includes some of the brightest engineers around.
Today's very important. It's our Jupiter flyby day. And of course, the test is coming right up. We'll see if the spacecraft made it through the dangerous radiation at Jupiter.
For this milestone in the life of the mission, all hands are on deck.
It's real big. As you can see, we have a lot of people coming in today, a lot of scientists who wanted this information off the satellite that we've been trying to get for them. So today is real eventful.
I would put it somewhere between launch and actually getting to Pluto. I'd say it's the third most critical activity in the whole timeline.
We're really putting the spacecraft through a stress test. That's our primary objective. But as long as we had to stress it, we thought we'd stress it with 700 science observations.
700 observations, 40,000 commands. Science planners work with guidance and control engineers to write a playbook for the encounter, a script for every time tick of the flyby. At Jupiter, New Horizons is on her own. Here on Earth, they wait.
You guys nervous?
No, not really.
Nothing we can do at this point.
That's right, not nervous.
No.
Not a bit.
This is all done by remote control. That's the nature of this business. 500 million miles away, our little puppy is doing its job and doing very well.
Just come up on track like it always does. So we're about a little less than 6 minutes away from our first look at telemetry.
They'll know all is well when screens light up with green text indicating the spacecraft has survived. DSN Australia confirms that New Horizons has phoned home.
Non-Pluto Ace.
Go ahead, Pluto Ace.
Yes, we're now receiving telemetry and we're logged.
RF mom on Pluto 1. Status check.
RF is green.
PI, this is mom on Pluto 1. Spacecraft telemetry for all subsystems is nominal. Spacecraft is outward bound from Jupiter, and we're on our way to Pluto.
Congratulations. All right.
Oh, relieved.
Go ahead,
we expected everything to go well, but it's good to know that it really did. Now we still have to wait for the data to come down, see what's happening with the radiation levels on our instruments, and waiting for that really good picture of Io that we should be getting in a couple of hours.
Good. Everything's looking really good at this point. The station's cooperating. No problems with the station. The spacecraft's in a good state. All's well.
Jupiter's not our ultimate destination. It's very nice, that we can actually get a lot of great scientific data for free, basically. We get that gravity boost, the most important thing, but after that, just getting that extra science and the extra practice for doing an encounter, which are really hairy. These encounter situations where it's all or nothing. You fly by and you don't return. We have to make sure everything works perfectly. So we're going to learn some lessons from this experience, apply them to the Pluto encounter, and hopefully make for an even better Pluto encounter.
The engineers could tell right away that all spacecraft systems were nominal. But the scientists wanted to see the very first pictures of Io. They'd gotten used to fancy computer graphics depicting an imaginary trajectory and volcanic plumes. But the actual images just in from Jupiter would determine scientific success or failure.
Yeah, this is the highest resolution image of Io with its spectacular plume, we hope.
Like Clyde Tombaugh decades earlier, they hoped for discoveries.
Flight right here. Oops.
The spacecraft took the images hours before, but for the researchers, this was exploration live and real time.
There it is off the, wow. Okay.
Camera and spacecraft delivered as promised.
2 plumes off the limb.
Okay.
Got both.
we got the night shipping.
Oh wow! Look at that.
Oh yeah.
And we got both of them. We got both of them.
And another plume.
Oh my gosh!
Rising into sunlight.
That's right, yes.
The first raw images might be fuzzy, but now they knew their aim was true. Computers would be able to clean them up and begin to update the textbooks.
Yeah.
Hal and John rushed next door to let the full science team see how their spacecraft was performing.
Second plume has a different shape.
Researchers called out requests to adjust brightness and contrast to reveal details hidden in the pictures. Now they knew for sure they'd captured the volcano called Tvashtar, spewing its sulfur plume 180 miles up into space.
How about that one up there?
What is that?
How about this one here? Is that a mountain or is that a mountain?
Many of the scientists were veterans of previous missions, but precise navigation and state-of-the-art cameras were revealing the Jupiter system as never before.
There was the one Voyager 1 image, the high-resolution image that showed the filamentary structure, but nothing like this.
Yeah, that's important.
Professional astronomers, of course, thrill at each new image, but the general public also had a role in targeting New Horizons cameras.
And what we actually did is went out to some blog sites where talented amateur astronomers and planetary scientists discussed the latest findings.
Like the student dust counter, this was the first time the public had a chance to shape a deep space mission.
We asked them, suggest to us some of your best ideas for what we call Kodak moments, unique geometries when we could obtain something evocative.
Out of this process came the idea for snapping Io and Europa lit edge on by the sun. Stern's favorite captured Europa rising over Jupiter.
It gives you that feeling that you're actually at Jupiter, and you have a view that you might not expect to have from a spacecraft, as if you were actually there, an astronaut making the flyby with New Horizons.
There were 7 Kodak moments, but New Horizons returned almost 700 observations.
And we have very detailed images that show us much finer structure now in Jupiter's ring system than had ever been obtained by any previous mission.
The cameras had been designed to work in the much dimmer light far out at Pluto, but special software helped record the structure and dynamics of Jupiter's clouds, including both the great and little red spots.
No spacecraft had made detailed observations since the formation of the little red spot. And this is not such a little spot, after all. It's as large as the Earth, practically. And we happen to be the first mission to Jupiter since the coagulation of some smaller storms into the so-called little red spot.
So the spacecraft passed this intentionally extreme stress test with flying colors.
Because I would have been very happy if half or more of the observations had worked out, rather than upwards of 95, 97%.
Leaving Jupiter, New Horizons will fly down the planet's giant magnetic tail, another first for this mission. Then it will be time for an 8-year cruise to Pluto, with long periods spent in hibernation, instruments turned off.
Well, Cruise for New Horizons is a 8-year sequence during which most of the time the spacecraft is in hibernation. And we do that in part to save money, but more importantly to save time, wear and tear on the electronics. In fact, most of the electronics boxes on New Horizons, although they will be 9.5 years old on reaching Pluto, they will only have between 2 and 3 years of on time. So for practical purposes, the spacecraft is not 9.5 years old, but 2.5 or 3 years old.
Just commands out.
Keeping the spacecraft young is one thing. Mission planners also had to think about who would be around to operate the spacecraft in 2015. Many of the faces you see around New Horizons are relatively young. That's also no accident.
You know, if it's something like that, let's say you have.
The project wants to make sure key team members are still on the job when the spacecraft gets to Pluto.
Yeah.
How old are you going to be?
In 2015?
Yeah.
I don't know, somewhere in my 40s.
Oh, and you're a youngster.
Yes.
If all goes well, even 2015 won't be an end date for New Horizons. It should have enough fuel to travel onwards, to rendezvous with 1 or 2 ice dwarfs beyond Pluto.
3, 2, 1.
The story of New Horizons may be a tale of high-powered rockets and sophisticated science instruments, but it's also evidence of human persistence, passion, and boundless imagination.
It's going to be an almost timeless object, that we're building something that will not only outlast the pyramids, but outlast the mountain ranges of the Earth. This will fly through the galaxy essentially unchanged from the way we build it, and it will be just that way for billions of years, literally. That's a stunning thing to me every time I think about it.
New Horizons is not just breakthrough science. It's another milestone in America's vision of space exploration.
Humans are explorers. I mean, we're not satisfied just to sit still with the status quo. We want to understand our place in the universe. We want to understand why we're here. Is the Earth unique? Is life unique? And science, and in particular space science, where we're going out to study the planets, is a very important component of that process.
Virtually every place we've sent a spacecraft on a first reconnaissance mission like this, that we find out that our Earth-based notions were flat wrong. So I'll tell you what we expect, but before anything, what we expect is to be surprised.
Exploring the outer solar system, because it's so far, takes a lot of time. We're talking decades rather than a few years. It requires a lot of patience, a lot of dedication, a lot of perseverance, but it's exciting. It's the frontier. It's the place that we know the least about, And yet the rewards could be huge in terms of what it tells us about the origin and evolution of the solar system. And because it's so far, we just want to know what's there. It's curiosity.